Signals by themselves are only half of the story in engineering. Every signal eventually passes through a device, circuit, or process that changes it in some way. Understanding how systems transform signals is one of the most important foundations of signal processing and RF engineering. In communication and RF systems, signals rarely travel directly from source to destination without modification. They pass through amplifiers, filters, mixers, antennas, channels, and receivers, each changing the signal in some way. These changes can affect amplitude, frequency content, phase, timing, or even the information carried by the signal. Without a systematic way to describe these transformations, engineers would need to analyze every circuit and device from scratch. This would make the design of communication systems extremely difficult, especially when multiple components are connected together in a signal chain. The fundamental problem is that we need a general framework that describes how inputs are converted into outputs, regardless of the specific hardware involved. This framework is known as a system. A system is any entity that receives an input signal, performs some operation on it, and produces an output signal. The operation may be simple, such as scaling a signal's amplitude, or highly complex, such as decoding information from a noisy wireless channel. In signals and systems theory, the internal details of the system are often less important than the relationship between the input and output. Engineers focus on understanding how the system behaves, rather than examining every physical component individually. Mathematically, a system can be viewed as a transformation. If the input signal is represented by xt, the system processes that signal and generates an output yt. This input-output relationship forms the foundation of system analysis. Intuitively, a system can be compared to a machine that receives something, modifies it, and delivers a result. For example, a coffee machine receives water and coffee beans as inputs and produces coffee as an output. In signal processing, the concept is similar, except signals replace physical materials. Physically, an RF amplifier provides a simple example of a system. A weak input signal enters the amplifier, energy is added from a power supply, and a stronger version of the signal appears at the output. The information remains the same, but the signal characteristics have changed. Mathematically, a system can be expressed as an operator acting on an input signal. For example, if a system doubles every input value, then the output becomes yt equals 2xt. This simple relationship illustrates how systems transform signals through defined rules. Systems are everywhere in RF engineering. Amplifiers increase signal strength, filters remove unwanted frequencies, mixers shift signals between frequency bands, and antennas convert electrical signals into electromagnetic waves. Each of these components can be analyzed as a system. Understanding systems allows engineers to predict how signals will behave as they move through complex communication chains. Instead of analyzing every component separately, engineers can model each block and combine them into larger system-level designs. At the system level, modern technologies such as Wi-Fi, LTE, 5G, radar, satellite communication, and software-defined radio are all built from interconnected systems working together. System analysis provides the framework that makes these technologies possible. The basic input-output description of a system is extremely useful, but it does not always reveal what happens internally. Two completely different circuits may produce the same output for a given input while using entirely different physical mechanisms inside. A common mistake is assuming that all systems behave in simple and predictable ways. In reality, some systems introduce distortion, memory effects, delays, nonlinear behavior, or randomness that require more advanced analysis techniques. This overview serves as the starting point for studying system properties in greater detail. The next topics, including linearity, time invariance, impulse response, and convolution, provide powerful tools for understanding how systems behave under a wide range of operating conditions. In this lesson, we learned that a system is any entity that receives an input signal, processes it, and produces an output signal. We also saw how system analysis allows engineers to model and understand complex signal transformations without focusing on every internal detail. In the next lesson, we will explore linear systems and discover why linearity is one of the most important properties in signal processing and RF engineering. If you found this useful, like the video, subscribe, and follow for the next lesson.